don't know how to do that because my stupid computer. Hello.
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 How do I get a JPEG image into a PDF image?
What
PDF
are you
isn't a
using
form
to
of
save a
image.
JPEG image with?
What?
How are you saving the JPEG image in the first place?
Well, in order to get the pictures, I have to take the pictures on my phone so that I can get them to my laptop, and that saves them as a JPEG. And then I can't figure out how to get them from a JPEG to a PDF.
What you can do is paste them all into a Microsoft Word document and then save the Microsoft Word document as a PDF.
Okay.
Does that make sense?
Yeah.
That's what I would do. Just make sure that once you save it as a PDF, open it and look at it and make sure that it's readable. It should be.
And you wanted us to turn these in somewhere in the class, right?
What are you talking about?
The pre-test thing?
Talking about the practice exam?
Yeah.
No, I don't care. Jennifer might want you guys to turn those in as part of the support course, but in terms of a grade in here, that practice exam is just for your practice and benefit. All right. So
Well, yes.
Jennifer's making people do those and getting feedback in the support course. Jennifer, are you around?
Yeah, please.
Okay, hi.
Yeah, Olivia, please do turn it in to the support course. Thanks.
I'm working on getting it from a JPEG to a PDF.
Yeah, and I can help you with that if you need help.
Jennifer, did you like my strategy? Is there a better way to do it?
It all depends on what technology everybody has. Everybody, you know, that's
right.
The problem.
I would use my laptop camera, but that camera sucks.
No, using a phone camera is great. So the ideal thing would just be to pair that with a phone app that could turn it into a PDF. But absent that, emailing the JPEGs to yourself and then using Microsoft Word to turn them into a PDF seems like a pretty good idea to me.
Where's my notebook? There's my notebook.
Hey, just forewarning, because it was in the news and actual credible news, not like in the news and you laugh at it because it's not very credible. Anyway, COVID cases are spiking again in Washington. So just be careful, get vaccinated, wear your mask. Love you all.
I already got vaccinated.
Why am I not surprised? I mean, I was hopeful that, oh God. Okay, yeah, not getting into it. I'm just
I'm just
as a retail worker, I am sad. That's all.
As a human, we should be sad.
Yeah, as a human, I'm sad. Like,
I'm not getting my summer job.
I don't want to get into it because the selfishness of the human nature is ridiculous.
My car, not arc. Oh my God, my brain. Read words.
My summer job just went out the window because other people are like, hey, let's COVID party.
No, gross.
I got 2 job offers, not interviews. These are places I worked for before school and stuff within the last like 3 weeks. And it's bizarre. I'm like, you want me in for an interview? They're like, no, we're offering you the job that you used to have back. If you're willing to work, we need people. I'm like, no. I'm going to school full time. I don't have time.
Yeah, I don't blame you on that one.
I don't want to hear that. I'm going to school full time and I work full time. You're gonna make me cry.
Well, and my chemistry teacher is kind of a tyrant, so it's like really hard. I'm just kidding, Dr. Moss.
I have been called a tyrant before, normally by people that were taking my majors level organic chemistry course. But
Oh,
in the
well.
reality, I was not the tyrant or the king of that course. It was the course itself. It's just one of the hardest undergrad courses you can take. So I did everything I could to make it easy, but it's not. It's a really hard course.
That's not the one I have to take, right?
Are you a science major? Yeah, you'll have to take it. Don't be scared. The person who teaches it here, Roxy, is amazing. So Dr. Smith, sorry. She's amazing. And I couldn't think of a better person for you to be stuck with if you had to take that class. And you'll learn a lot. And as a gate course to pre-med, pre-health kinds of things, it's really important for med schools to have information about what happens to students when they're presented with a huge body of unfamiliar information and a fair amount of stress. And that's what organic chemistry is. So there's a reason why med schools and physician assistant schools look at people's grades from OChem as one of the first things that they look at when they're looking at an application packet. It's crazy, but it's absolutely true.
I remember that.
And I'm happy to help if you ever need help with organic, because I miss teaching it.
There you go. You got a
Hey,
pocket
Kat,
teacher.
this has nothing to do with Chem, but I just wanted to say your hair looks lovely today.
I had to go in public today,
Oh,
so it's done.
well, it looks super cute.
Wow.
Don't ever do my hair even when I have to go out in public.
I just trimmed up my side, like it was super fuzzballing, so I did a 3 and just shaved that. But other than that,
You guys are all done with your problems, right?
no, I'm still working on
Okay,
it.
so let's kind of keep the chat down a little bit. Sorry, I'm having a hard time focusing. Thanks.
Thank you for keeping us on track, Jennifer.
I was about to say something too.
Speed and feet. Oh, shit.
So even if this seems easy to you, try hard to be very, very intentional about setting up the problem in steps so that you can see the units cancel. All right. So when you're driving in your car, most of the time, you don't think about the speed that you're driving as a fraction with a unit in the numerator and a unit in the denominator, but it certainly is. This is the number of miles that we travel per every hour that we're driving, if that's our average speed. So can we convert this unit, miles per hour, into a unit of feet per second?
Yes.
Sure we can. We know that in the numerator, our unit for distance is currently miles. We're going to convert that to feet. In the denominator, our time unit is currently hours. We need to convert that to seconds. So let's make sure that we can figure out how to set up the units to do that. Now, I'm a big fan, especially if you're stuck, of not even bothering with numbers at the beginning, just thinking about the units. So I gave you the conversion factor to convert miles into feet. But in order for the units to cancel, we need feet in the numerator and miles in the denominator. If you chose to convert the denominator first to go from hours to seconds, whatever, you'll get the same place. All right, it can be done in either order. So once our units cancel out from that conversion factor, we should have feet in the numerator and our miles have canceled. Now we just have to add conversion factors to convert those hours in the denominator into seconds. So unless you know how many seconds there are in an hour, and you could do that in one step then. Turns out there are 3,600 of them, all right? But if you didn't know that, you could convert in 2 steps instead. Because we know how to convert from hours into minutes. Oops, I did that wrong. So I need minutes in the denominator and hours in the numerator to cancel out with the hours that are already in the denominator. And then we're going to convert from minutes in the denominator to seconds in the denominator. So those conversion factors should cancel out to give us final units of feet over seconds. Now we just have to fill in the numbers and then punch it into our calculator. So we know that there are 5,280 feet in every 1 miles. That's a conversion factor we got right from our problem. We know in every 1 hour, there are 60 minutes. We know that in every 1 minute, there are 60 seconds. So when I put this into my calculator, I end up with 66 feet per second. If you don't end up with the same thing, you probably multiplied by something you intended to divide by. Remember, in a multi-step problem like this, an easy way to do it, there's actually 2. I think Jennifer's favorite way to do this might be to multiply by everything in the numerator and then after that divide by everything in the denominator. I don't do it all my multiplication first and then all my division. I just go step by step. So this times this divided by this times this divided by this times this divided by this. In the end, if it's in the denominator, we're dividing by it. If it's in the numerator, we're multiplying by it. All right, second one is just a little bit harder. So if we know how many miles per hour we were driving, it's 56.7 miles per hour, and we know how long we were driving, 778 minutes, we should be able to use those two things to figure out what distance we drove. Because miles per hour times hours would give us miles, a distance in miles that we drove. The unfortunate thing is we are not presented with hours, we're presented with minutes. So we got to convert to hours first. Now, if we start with minutes and convert to hours, we should be able to use our speed as a conversion factor to convert into a distance in miles. And once we know what distance we traveled in miles, we should be able to use our fuel economy as a conversion factor to convert into gallons of gas. So that is the strategy that I'm bringing into this problem. If you did something in a different order, you can totally do that. All right, you could approach this problem starting from the miles per gallon. It's just a little bit weirder to do it that way, at least in my opinion. But everybody's got one of those. In order to get our units to cancel the way we want, our conversion factor here should have hours in the numerator and minutes in the denominator. And then after that, to convert to miles, we should have miles in the numerator and hours in the denominator. And then to convert to gallons, we should have gallons in the numerator and miles in the denominator. So let's fill in those conversion factors correctly and figure out what our number of gallons of gas we burned is. All right, so this one we all know, in every 1 hour, there are 60 minutes. This conversion factor comes directly from the problem. It tells us how many miles we went each hour that we were driving. And this conversion factor also comes from the problem. In the problem, it says that my car burns 1 gallon of gas per every 27.5 miles that it drives. How many sig figs should I keep for my answer here?
Three?
It looks like my minutes was read to 4 significant figures, my speed to 3 sig figs, and my fuel economy to 3 sig figs. We're multiplying and dividing, so we have to round to the same number of significant figures as whichever one of them has the least, so we should round to 3 sig figs. When I round my answer to 3 sig figs, I get 26.7 gallons of fuel. Oops, I actually forgot to put the 778.7. I just did it as 778. So the answer, if you started with 778.7, is going to be slightly more gallons than 26.7.
26.8.
In the end, it's 26.8.
Yeah.
Okay. In the end, the number of minutes that we're traveling isn't the important part. The important part is, do we see how to set up the conversions step by step to get from what we're given in the problem to what the problem is asking us about, right? So we can use conversion factors from the metric system that we know, like prefix changing, or sometimes the unit conversions come from the problem or from a definition, like density is a conversion factor that we learned about in chapter 1 that lets us convert back and forth between the mass of a sample and its volume. I bet you never thought about density as being similar to speed, but in a way they are. They're both conversion factors that let us convert back and forth between two very different units based on what we know about a system. Pretty awesome.
So I have a question.
I'm okay, I might have an answer.
So I don't know if you can see my screen or not, but
Let me unshare really quick.
so if instead of putting all that together in one equation, I broke them up into smaller steps and just
Yep.
said, okay. My question is, when can I start rounding? If I start rounding too soon, it's going to mess up my final answer, right? So,
Right. Yeah, the right answer is we don't round until the very last step.
okay, so if I do
So
it,
what I would do is I would use
I
what my calculator put
Yeah.
out as the input for my next step,
Mhm.
rather than rounding and then using that as the input for the next step.
So if I do it this way, I need to keep all of these decimals when I write them down. Otherwise, I will be off by.
Theoretically, yes. In practicality, if you know you're keeping only 3 significant figures, if you carry 6 through each of the steps and then round, you're not going to end up with a mistake. Does that make sense?
Yes.
So the best practice is to keep all of them. In reality, as long as you keep a couple more than the number of sig figs you need at the end, then you'll be okay.
Yeah. This is a common I don't want to call it a mistake, but it's a common thing that we do. If we break this up into smaller things, we'll say, oh, this is just 12.97, and then I'll say this is 12.97, and then if I round too soon in my calculations, I'm going to be off by a little bit. And so that was my question. Thank you.
And the good thing is, like, would you be off by enough that I wouldn't recognize your answer as coming from a correct thought process? No. So if I was in a really bad mood, like I probably am going to be when I'm grading these because I've got so many stinking things going on right now. If I was in a terrible mood, I might take off 1 point out of 10 for a rounding error like that. In reality, the more likely thing is I'll just give you all 10 points and write on the exam, you shouldn't round at intermediate steps.
Yeah, Alex will not forgive you.
No, Alex is not as forgiving as Dr. Musk is. That's true.
So if you're having trouble with Alex being off by a tenth or something like that, it might be due to rounding intermediary steps. So,
and the other place, once we start doing calculations from the periodic table using average atomic masses, make sure you use Alex's periodic table, because if you use a different one, even like the one that I have printed on our Canvas page, then it might not have the exact same entries for the average atomic masses, and that little change can sometimes make a difference. 99% of the time, it's not going to make a difference. Well, cool. I have tried over the 3 mini worksheets this week to give you guys plenty of extra practice with the kinds of questions that students tend to get to exam 1 on and be like, I can't do this at all. So I'm going to lose 10 points out of the 100 because I can't do this free response question. All right. There are other kinds of questions that are common ones that students mess up on. I've tried to include a version of those on the practice exam as well. All right. So you guys have plenty of insight into the kinds of questions that you're going to be expected to answer on exam 1. Juliana.
I would like to point out that you also, if the practice things aren't helping or whatever, there's also the review function in Alex.
There is the review function in Alex, right? So you can go back and click on review, and then after that, it will let you do extra examples of any of the topics that you've already completed from chapters 1 through 3. So That's a great tool as well. So the best that I can do is just give you guys lots and lots of resources that you can use and be as clear as possible in terms of what I expect you to understand for exam 1. And the practice test, in terms of the principles that the exam 1 is going to cover, the practice test is an old version of the real exam 1. So if you know beyond any shadow of doubt that you just nailed the practice exam 1 to the wall and got all of them, then you're going to be in great shape for the real exam 1. The questions won't be the same, but I promise you the principles that the exam covers will be the same principles. And it's really hard to get 100% on one of my tests anyway. All right, I'll just say that right now. If we were actually in class together, one of the cool things that I like to do, and I don't really get to do it in the virtual environment, is when students get 90% or better for a raw score on my exams, they get stickers on their exams, and they're really cool stickers. I spend money on like high quality, amazing stickers instead of just perfunctory stickers.
If I get a 90 or better, I will stop by the college, to pick
yeah.
up a
I'm
sticker.
gonna need a
I actually,
sticker.
it's been so long since I've been to my office, I can't even remember where the stickers are anymore. I'll have to look around for them.
I'm gonna need a sticker if I get that good of a grade.
Yeah.
Same. I'm gonna need a sticker.
Yeah.
And it'll go with the rest of them on my.
I'm right across the street from the college. If you need stickers, yeah, just hit me up.
No, I enjoy buying them. So anyway, you will definitely, even in the virtual environment, I still grade by hand on my iPad. So you'll get some sort of like congratulatory message on the first page of your exam if you get 90% or better, like woot or yes or OMG or something like that. Or sometimes just like a surprised face, especially if it's like 100%, like. So look for that and go after it, right? So I want to give as many of those congratulatory messages on exams as possible.
Oh my gosh, I need the little shark
It's
sticker.
a whale shark.
Yep,
Oh!
that's one of the back when Jennifer took the class for the first time, she got stickers on all of her exams. So I hope that's not a FERPA violation since you weren't like a traditional student taking the class. But yeah, cool stickers. I think that's one from Dory.
And they're,
Yeah,
they're
yeah,
split and they're shiny and they're 3D.
that's destiny.
High quality stickers. So that's one of the things I'm going to be really excited about when we get back to in-person exams, especially. For one, I can go back to not making them open book, open note. And that actually makes the exams a little bit easier because I know that you have to know more things like in your head. But I can go back to stickering the ones that deserve stickering. So I'm excited about that. All right. So our other big job today, other than doing our last mini review for chapter 3, we have to, oh my goodness, there's another
Hank.
one. Yeah, they're really good. I had Avengers ones also, and the Avengers ones were like huge. I had a pack of just random Disney ones that were like as big as my fist. They took up like a quarter of the page. Yeah, they were awesome. So, all right. So our job today is to continue our discussion of Lewis structures.
I'm getting real good at them because I did review yesterday on Alex to
Good.
really get
That's
better.
awesome. I think you will find that my 3-step method is the easiest way to learn to draw them right, at least at the level that we're drawing them in this class. There are a couple of more steps that we can learn that help us, like once we have a basic Lewis structure, sometimes tweak it to make it even better because of violations of the octet rule. So first of all, I want to introduce you to one atom that very consistently, or at least fairly consistently, violates the octet rule. There are lots of atoms that do it, but we're going to learn about one just as a token example in this class. Juliana.
I'm gonna take a wild guess and say it's sulfur.
It's not sulfur. The reason why is because the way that sulfur violates the octet rule is weird. All right. So if you were in the majors class, I would explain to you why sulfur and lots of other elements that are in the third row or lower on the periodic table can violate the octet rule. But because this is a non-majors class, we're just going to look at a couple of examples of Lewis structures that violate the octet rule and
Helium?
understand at a basic reasoning why they do that. All right. So I want to look at this Lewis structure. And I want to look at this Lewis structure. So try your best to draw those Lewis structures where we don't violate the octet rule, right? Where we follow Dr. Musk's 3 rules. And let me stop you before you even start writing this Lewis structure because it's a trick, all right? This is like the Admiral Akbar, it's a trap thing. If we look at how many valence electrons, right in step 1 of our 3 steps. Step 1, total up our number of valence electrons. Step 2, draw a skeleton structure. Step 3, fill in the remaining electrons to give all of the atoms an octet. Step 1 tells us that this is going to be a violation of the octet rule. The reason why is when we total up our number of valence electrons in NO2, nitrogen has 5, each of our 2 oxygens has 6, so 12 plus 5 is 17. I don't know why I wrote that as 12, 17 valence electrons. Right now, we can tell that this is going to be an octet rule violation. It has to be. Why?
Because it's not in a multiple. I mean, like it's not a multiple of 2. So
What do we call those kinds of numbers that are divisible by 2, Sarah?
Yeah,
even numbers, right? It's an odd number of electrons. No, it's fine. I was just teasing you a little bit. I'm sorry. I had to do it.
I'm like 17's a prime number.
Like, yeah. How could we like complicate the explanation of what kinds of numbers we're talking about? So an even number of electrons means that in the end, one atom in that Lewis structure is either going to have only 7 electrons around it, or one atom is going to have 9 electrons around it. There's no way to get a perfect 8 around each element when we have a total of an odd number of electrons. So any Lewis structure with an odd total number of electrons, you can recognize that it's going to be a violator of the octet rule.
So where am I putting my spare electron?
You're not. You don't even have to draw this Lewis structure. I would recommend that you not draw this Lewis structure.
But I already did.
I can show you kind of what it looks like, but it's something that's going to be very dissatisfying. So I'm not going to do it.
Okay.
All right. Now I want you to do your best.
If he doesn't see it.
And I will tell you that the Lewis structure that you are likely to draw for BCl3, following our 3 rules, is going to be an incorrect Lewis structure. All right. I'm telling you in advance so you don't get mad. Remember, this doesn't follow the octet rule. How many total electrons did you count up for BCl3? How many total valence electrons?
10.
I got 24.
24. So if you're still confused about how that works, I'm looking at boron and seeing that's in group 3, which gives it 3 valence electrons. Each of the 3 chlorines is in group 7, which means each one of those has 7 valence electrons. So 7 times 3 is 21 for the 3 chlorines, and another 3 for the boron gives us 24 valence electrons. So this Lewis structure has to have exactly 24 valence electrons in it, no more, no less. Skeleton structure, hopefully you did the reasonable thing, and because boron was listed first, assumed that all of the others would share at least 1 covalent bond to that central boron. That used up 6 electrons. We have 18 left to assign. 2, 4, 6, 8, 10, 12, 14, 16. We only have 2 electrons left to put into this structure at this point. And at this point, boron is short 1 pair of electrons of an octet. Chlorine is also short a pair. So hopefully, if you were following the 3 rules, you would have decided, I'm going to make the last pair of electrons another shared pair between boron and chlorine so that both of those have an octet. Unfortunately, boron is a known flagrant violator of the octet rule.
Send him to octet jail.
And this is in the topical videos, but it's important enough that we do an example of it together just to make sure that you understand that some atoms just don't like to follow the octet rule. So boron tends to have 6 electrons around it instead of 8. What does that mean? That means that when we got to this place, so I'm going to rewind just a little bit here. When we got to this place where these 2 chlorines had an octet, this chlorine was short a pair and that boron was short a pair, and we only had 2 more electrons left to assign, we should have just assigned them to chlorine because boron prefers to have 6 electrons around it instead of 8. So it turns out that this is the best Lewis structure for BCl3, not this one, because boron's a weirdo. And what's really weird in terms of reactivity, you've all met one of those people. We're not going to name any names in front of the group, but you've all met those people that, like, when they don't get what they want, they're really unhappy. And then when they get what they want, they're still really unhappy. That's boron.
Brats.
Yeah. Boron is incredibly unhappy all the time. And unhappy is chemistry lingo for reactive. So when boron is like this with 6 electrons around it, it's not very happy. And the reason why is because all atoms naturally want to work towards some kind of an octet. So boron is short of an octet here, so it's not very happy that way. If you give boron an octet, there's another reason that we don't talk about in this class that makes boron unhappy when it has an octet too. So boron is one of those elements that's really hard to keep stable because it either wants to add 1 more bond to get an octet, or it wants to lose a bond because it would prefer to have 6 electrons around it instead of 8. So no matter which thing you do, it wants you to do the other thing instead. So boron is very, very unhappy. Yeah.
So it's the cat from Jackson Galaxy's My Cat from Hell.
Yes. Yep. Boron is a clinically unhappy element. So I want to review something that we learned about last time we were together. All right. We looked at this Lewis structure, the Lewis structure for carbonate. So carbonate has the chemical formula CO3 with a -2 charge. And if you look at my Lewis structure, you will see that each of the atoms in the structure has a full octet. And we have used exactly 24 electrons, which is how many total valence electrons CO3 2- has. So 4 from carbon plus 18 from the 3 oxygens is 22, plus another 2 for the -2 charge gives us 24 valence electrons. Now, depending on your style, you may have decided to share that extra pair of electrons with this oxygen instead of this one. Or you might have chosen to share that extra pair of electrons with this oxygen instead of the other 2. I think we would all agree that all 3 of these Lewis structures are correct Lewis structures. Each of the atoms has a full octet. Each one of the Lewis structures has exactly 24 valence electrons in it. So in cases like this, where there's more than one Lewis structure that fits, all right, there's more than one way to assign the electrons in a good Lewis structure, the reality is that no one of these Lewis structures actually represents this molecule. So when I look at carbonate, what I see here is a double bond and 2 single bonds, right? There are actually chemical ways that we can check to see what kind of bond there is between 2 atoms in a molecule. The primary tool that we use is a measurement called bond length. All right, I'm not going to bore you with how we measure bond length in chemical systems, but it turns out that single bonds are always longer than double bonds between the same 2 atoms, and double bonds are always longer than triple bonds between 2 atoms. Yes, there can be triple bonds. So we'll do an example of that today. Now, if this Lewis structure was a correct Lewis structure in terms of telling us about the chemical truth of carbonate, what we would expect to see when we looked at carbonate in terms of bond length is 1 shorter carbon-oxygen bond and 2 longer carbon-oxygen bonds. Because 2 of the bonds look like single bonds to us in a Lewis structure, and this one looks like a double bond. It turns out that when we measure the length of the carbon-oxygen bonds in carbonate, this bond is exactly the same length as this bond. And that's exactly the same length as this bond. All 3 of the bonds in carbonate are identical. I know. This is a quirk with the way that we draw Lewis structures. In each of these Lewis structures, what you've done is you've taken each pair of electrons and assigned it to just one location, either as a pair that belongs to just one atom or as a shared pair of electrons that belongs to 2 atoms. It turns out that not all electrons belong to just 1 or just 2 atoms. There are some times where electrons can inhabit more than one location all at the same time. So we can't do that. I would love to be out fishing and teaching at the same time. I can't do that. I can't be in 2 places at once. Electrons are real small and real fast. They can be in 2 places or even 3 places at once. So the way that we show that is by writing in arrows like this between these 3 structures. We call these 3 versions of the carbonate structure 3 resonance structures. So carbonate and lots of other molecules where we can draw more than one way of sharing the electrons, they have this thing called resonance. And what that means is that electrons are being shared over more than one bond location all at the same time. So this bond that's being shared, the second bond between carbon and oxygen here, isn't just being shared between this carbon and oxygen. That second bond is actually being shared between these 2 atoms as well, and between these 2 atoms. One way to think about this is The reality, the real life structure of carbonate is like an average of all three of these at once. So that gives us some really weird things when we start to think about what is this bond between carbon and oxygen. It's not a single bond. What is this bond between carbon and oxygen? It's not a double bond. If it's an average of all three of these structures, then what we end up with is 1, 2, 3, 4 total bonds that are holding the carbons to the oxygens in carbonate, 4 bonds that are shared across 1, 2, 3 bond locations. So what that tells us is that in reality, this bond between carbon and oxygen is not a single bond, and it's not a double bond. In fact, it's a 1 1/3 bond. You can think of it as that one extra bond being shared over all three of those bond locations. And anytime we have Lewis structures where there's more than one correct way to draw the Lewis structure to fulfill the octet rule, we end up with this thing called resonance, where we have to think about all the versions and then in our head know that it's an average of those. All right, here's another example. We looked at this Lewis structure last time we were together. This is the nitrite ion. This is not NO2, this is NO2 minus. So we do have an even number of electrons here, 18 total electrons in the structure. Is this the only way that we could share the electrons to give all the atoms an octet? Well, obviously not, or else I wouldn't have used this as an example. You might choose instead to have a single bond to the oxygen on the left and the double bond to the oxygen on the right. If we were to examine the bonds according to bond length in this molecule, what we would see is not a shorter and a longer bond, but instead 2 bonds that are exactly the same length. So whatever we think about the nature of these nitrogen-oxygen bonds, this bond is identical to this bond. The Lewis structure doesn't show that. We have to think about it as an average of these 2 resonance structures. So if I was to define the idea of resonance, what I would say is resonance is when electrons are shared over more than one bond location. There's lots of ways to define resonance, but in general, all of them talk about electrons being in more than one place at once. So very often we use the term, I like the term, but non-majors don't tend to like it. Delocalized electrons. That's the stuffy chemistry word for how we think about the electrons in resonance.
Because
so electrons that can be
still,
shared.
right?
What's that?
Because it won't stay still, right?
It's not about staying still. It's not that this is a double bond and then this is a double bond and this is a double bond and the double bond moves really fast. That is not resonance. The reality of resonance is there is no double bond and there is no single bond in carbonate. We cannot think about just one of these pictures of carbonate as being sufficient to tell us what the bonds in carbonate are like. We have to think about it as an average of all 3 of these at once. So because this bond is a double bond in one of the 3 pictures and a single bond in the other 2 of the pictures, on average, what that tells us about that bond is that it's a 1 1/3 bond. There's just no way for us to draw a 1 1/3 bond in a Lewis structure. So when we draw a Lewis structure for something like carbonate, even though it looks like there's a double bond and 2 single bonds, you have to know in your head, I could have put that double bond any one of those 3 places, which means in reality, that's actually a 1 1/3 bond, and so is that, and so is that. This is something we have to think about when we draw Lewis structures that have multiple resonance forms. So what would the bonds look like in nitrite? If we have 3 bonds averaged over 2 bond locations, those bonds between nitrogen and oxygen in nitrite are 1.5 bonds. If this is dissatisfying, stew on it for a little while. All right. This is like a sort of deep, almost philosophical chemical truth. The idea that electrons can be shared over more than one bonding location at a time. An electron pair can be in multiple places all at once. This is not something that relates directly to the real world because we can't do that. I can't be out fishing and teaching and grading all at the same time. But a pair of electrons can be here and here and here all at once. That is the idea of resonance. That's an important thing that it's in the topical videos, but I wanted to give us a little bit of time to like think and talk and practice with it because it's a pretty theoretical concept. This is something that a lot of high school chemistry teachers completely flub the way they describe it because they don't understand it well. They think it's like the double bond just moves around really fast and it's sometimes here and sometimes here and sometimes here. No, that is not what resonance is. All right. You cannot take that pair of electrons and confine it to just one bonding location. It belongs to all 3 of those bonding locations at the same time. I know it's hard to think that way, but that is your charge. You have to think that way. Get used to it. Right? How do we learn something difficult? We just get used to it after a while. So you'll get used to this.
That's a motto for everyday life, not just chemistry.
Yep. So I wanted to get to the point where we were discussing all of the different shapes of molecules by today. We didn't get there. It's already almost 6 o'clock. So as long as we covered resonance today, that's probably good enough. Next week on Tuesday, we will talk about the shapes of molecules, and hopefully if we have time, we'll practice not only identifying the correct shapes of molecules, but being able to tell whether they are polar or non-polar. So those are the last topical videos from chapter 4. Make sure you watch those before next week. I would assume that you're probably going to be watching those like on Monday because you're probably going to be taking the exam sometime this weekend and then trying not to think about chemistry for a little while. And that's totally cool. Any last question about exam format or?
So you're going to be on at 5 tomorrow for just.
Yes. Yep. I thank you for reminding me because I wouldn't have said anything about it today. And I'll also put an announcement out on Canvas about that so people are sure. Now, if you want to, if you feel like I am stinking ready to take this exam and come tomorrow morning right at 8 a.m., I'm taking it and getting it over with. Great. Do it. The exam will be open for you to take at 8 in the morning tomorrow. It will be open all the way until midnight on Sunday night. All right. You can take it any time in that span. Budget 2 hours, so don't start it at midnight on Sunday. Start it no later than 10 p.m. on Sunday, all right? But we will have time tomorrow to do one last exam study session. We can do more practice problems. We can look at practice test problems. We can look at whatever you want to. Now, what I will tell you is I'm not going to make a worksheet for that. I'm not going to have any prepared problems for that. I am going to rely on the people that attend that session to tell me what they need more help with. I can make up problems, but you got to tell me what kind of problems you want to do, and we can make them up. So that'll be 5 o'clock until whenever, probably an hour tomorrow.
And then is the test like you open I keep wanting to call it Canva. You open Canvas and it's like you have to leave Canvas open while you're doing it. Is that
Nope.
from the same way? Okay.
Nope. It's not a test that uses Canvas directly.
Hmm.
You will end up, after you digitally sign your honor code, you will end up opening just a PDF of the test. You'll get a PDF copy of it, and you can either just keep it open and then write your answers on blank paper, or you can print out a copy of the exam and then take the exam just like it was an in-class exam on paper.
Okay. So we're basically signing the honor code that we spent no more than 2 hours and that we're not
No,
cheating.
I can tell if you spent more than 2 hours. That's easy. So the honor code says, I promise that I have neither given nor used any unauthorized resource on this
Oh,
exam.
okay. Oh, so okay.
Which means that you didn't talk to anybody else in the class about what was on the test at all, and you didn't Google search while you were taking the exam, right? Those are the two ways that you could screw yourself over. Knowledge transfer to other students or Google searching while you take the test.
Okay.
And I'll only say it one more time. I'll be able to tell if you Google search on the test, all right? So don't do it. I literally had to fail 2 students last quarter because of that. I don't want to do it. You know it by this point, like, I'm not a terrible person. I don't delight in failing students. As a matter of fact, that like really bothers me a lot. It's the worst part of being a teacher, is to have to deal with when students do dishonest things and you've got to hold them accountable for it. It's terrible. So don't make me be that person, because I don't want to be. Jennifer, is that about right? That's a pretty terrible part of the job, isn't it? Is Jennifer not here anymore?
Yeah, I'm here.
Isn't that a terrible part of the job?
Yeah.
Okay. Yeah. So we don't want to be the bad people at all.
Well, I'm gonna probably come tomorrow and I'm gonna want to do more like addition and subtraction, multiplication with significant figures, because that's where I
Okay.
messed up royally. It's like the
Okay.
easy stuff on the practice exam.
Remember that no matter how many examples of those that we do, the principle is the same for every one of them, right? Whenever we're multiplying and dividing, we round to the number of sig figs, as whichever measurement has the least sig figs. Whenever we add and subtract, we round to the number of decimal places, as whichever one has the least number of decimal places.
Okay.
And yes, Jennifer, that is an oversimplification, but it's for what we're doing in chemistry, that's good enough for us. All right. I tell you guys lots of lies, but at least I'm honest when I'm lying to you. When I tell you the whole truth, I'm honest about that.
And I'll be there tomorrow for more conversion factor problems for sure.
Yeah.
Mm.
And
Oh,
I'll tell you, conversion factors are going to be on exam 1, and they're also going to be on exam 2 and exam 3. You don't ever get rid of those, because we constantly have to tinker with units to get them to cancel out, to move toward solving problems in the world of chemistry. So unit conversions are how we solve most of our problems in the world of chemistry. So we got to understand how to do them. And that's why I've been practicing. You've seen we've had at least 1 conversion factor problem or 2 on every one of the practice Quizlets, right? So it's really important. That's a skill that's like not going away ever for the rest of the class.
Dang it.
no, but in the real world, like when you're a scientist, like don't you use like, undergrads to do that kind of grunt work?
No. You think I would rely on somebody else to do my calculations for an experiment? So if I was a principal investigator at a Research 1 college, a Research 1 university, then yeah, my students would be doing some of those calculations, but I'd be checking them over for sure. And a lot of times the calculations get hard enough that it takes multiple heads sometimes to think about the best way to represent the data. And really, when we're learning how to do these level of calculations, it's sort of just preparing us for places where it's not nearly as clear about how to get to an answer.
I don't want to think about the longer ones. I think that's what it is.
But the ones that we're gonna do in the longest kinds of problems that we'll do will be maybe 5 or 6 steps. And really, it's no more difficult than the ones that we've done so far. It's just, what conversion factors do I know about in this problem, and how can I use them to change the units into what I need for the problem? That's it. So you can use that strategy for any problem where you're thinking about conversion factors. What conversion factors do I know? What information am I given at the beginning? And how can I convert it into what the problem is asking for? Or if it's not a problem anymore, if you're in your professional career, how can I convert it into the thing that I want to know about from my experiment? So Jennifer posted a link to the office hours. Do you guys want to stick around here, or are you guys just going to peace out there right away?
I have a math test.
Okay.
I
I gotta go do some nutrition homework.
I gotta go run some errands with the husband.
Jennifer, I'm going to hand it off to you, but I'm assuming you guys are just going to peace out and go over there in a minute. I don't think I can anymore. Jennifer doesn't look like she's on the list.
Well, you all have a good night and good luck with the exam, everybody.
Good night.
All right.
Y'all
Yeah, I'm
around.
just
On a
I'm gonna
sticker.
close the meeting out. Have a good evening, everybody.
Bye.